we reviewed. Let us review what we have done from yesterday. Review of lecture 14. In yesterday class, we talked about tolerances, and we said that tolerances is quantified using two important things. One is fundamental deviation, and other is magnitude of tolerance. We know that capital A, B, so on, capital letters, uppercase for hole, and lowercase letters for shaft is used. And similarly, magnitude there are 18 grades for different diameters. That is also shared to you in the last class. So using these two things, we try to quantify the things. And there are two ways to quantify it, either using hole basis system or using shaft basis system. Right? And mostly the hole basis system is used because we use standard drills or reamers to drill the hole, whereas the shafts can be rounded arbitrarily. So that's the reason we just prefer the kind of hole basis system in most of the cases. Next, we also talked about different kinds of fits based on the tolerances. We said that there are three types of fits. The one is clearance fit, where we have positive tolerances or positive clearance, and interference fit, where it is positive interference, and there is transition fit, which do depend upon the actual tolerances what you see in the parts. Okay, so those are the things which we have reviewed in the last class, and in today's class, as we promised, we'll go to the design for the dynamic loads. So even before I start this topic, the one key important thing one has to remember is most of the material are bound to have defects coming from manufacturing or materials and other stuff. And or people, because of the design, you need to create some certain service ports or something like that. So these all creates inhomogeneity in the structures, and these kind of inhomogeneities results in the stress concentrations, especially for the dynamic loads. These are quite most important when compared to the static loads. That's the reason, even though there is kind of factor of safety involved in it, we take higher factor of safety in case of a dynamic loading, because it is the structures are more vulnerable under these inhomogeneities. Okay, so the main topic that we will discuss in today's class with few example is mostly on the stress concentration. So we know that so far when we are designing it, we used a lot of fundamental equation or the elementary equations. So let's review it again. So in stress analysis, we made use of these are fundamental or elementary elementary equations for we used sigma t is equals to P by E. Under bending, we said it is sigma B is equals to M by I. Under simple shear, under shear, we said tau is equals to P, tangential force divided by area. And under shear coming from the torsion, we said that it is equals to T rho by J, where T is the torsion involved. So these are the fundamental equations we generally used for the stress analysis. But one has to understand that these equations assume that there are no discontinuity in the cross section, because they are elementary in nature. They don't take care of it, but that would pose problems, especially when you're doing the dynamic analysis. So in practice, discontinuities are unavoidable due to defects or certain features such as oil holes, grooves, keyways, splines, screws, screw threads, and shoulders. So in these cases, the elementary equations fail to provide conservative estimates, that is in the presence of discontinuities in which cases stresses can be much higher. Further, stress concentrations is defined as the localization of high stresses due to irregularities present in the component and abrupt changes of cross section. And stress concentration factor are employed to get an estimate of the localized stresses at the discontinuities. So in this chapter, what we will see is we will try to see in which causes different types of which causes the stress concentrations, and how the correction factors is employed using some tables and charts. And using this, what we will do is we will try to implement those charts in designing the structures with inhomogeneities. Okay, so today we will also do a couple of examples to understand the stress concentration in much better form. To start with, the causes of stress concentration are first one, variation in material properties, and this can be because of internal cracks and flaws like blowholes or non-metallic or foreign inclusions. Second, load application at a point. So generally, if you have point loads, under the point load, the resisting area is close to 0, tends to 0, so it would shoot up the stresses. And these things occur such as contact between meshing teeth, cam and all over balls and races in bearings. Rails and wheels. Crane hook and chain. Are some of the examples for the point load situations. The third can be abrupt changes. Changes in section. So, such as steps are cut in order to mount gears, and pulleys and things like bearings on transmission shafts. Next one is discontinuity. Now, in this case are generally like oil holes or grooves, keyways, splines, and screw threads are the design. And sometimes you can also have, because of machining scratches, and stamp marks in forging, inspection marks, surface irregularities. So these are the causes for the stress concentration factor. Now, what we'll do is we'll define what is stress concentration factor in the kind of theoretical form. Okay. Which is defined as capital K. T is defined as highest value of actual stress near discontinuity divided by nominal stress. obtained by elementary equations for minimum cross section. So that can be written as sigma maximum stress that you have seen on the component divided by sigma naught, or tau max divided by tau naught, where these numerator, the actual highest stresses in the component, and sigma naught or tau naught are obtained through the fundamental equations which we have seen here. These are the sigma naught or tau naught obtained through this elementary equations. So how does we determine these stress concentration factors? So the theoretical stress concentration factors are determined by using mathematical method based on theory of elasticity for the elastic component, but sometimes you can also use theory of elastoplastic also if the material starts yielding. Next thing is experimental methods on similar discontinuity in epoxy resin component, not on actual component. This will only give the geometrical form. If you do it on the actual material, you can also get because of the material variation, but that would be too much. Variations are involved by the both the things. That's the reason generally they are done on a epoxy resin with the similar discontinuities. The third one is to do a full-fledged finite element analysis for a given shape or discontinuity. So irrespective of which method is used, stress concentration factor is called theoretical stress concentration factor. Now we will see how to kind of reduce this stress concentration factor for certain scenarios. For example, one scenario is, so the topic is reduction of stress concentration or just stress concentration. So in this case, for example, I'll put the picture. So if you look at here, so in this section, so when cross section of the channel as shown here is suddenly reduced, the velocity increases in order to maintain the same flow. So this is a simple case of a pipe with a flow, and there is an abrupt change in the cross section. When you see an abrupt change in the cross section, here the incoming and outgoing, if you have to maintain same, that means it has a higher area and the velocity will be some v. But if the area is reduced, in order to meet the same flow output, the velocity has to be increased. Okay, so automatically what happens? Streamlines get closer to each other, and at the bend at this place, and they get kind of, so streamlines bend at the abrupt changes and become narrower and crowd together. So this crowding up is similar to, so if you look at, instead of this pipe flow, you can assume that this is a material, solid material, and you have loading it with the stress, the tensile or the stress waves or the stress lines would also follow the similar path. So whenever you have a narrower part, that means the stress concentration has been absorbed, compared to when you have in a farther spacing, it is like lesser stresses. So if you reduce further and further cross section, the stress lines or the flow lines become closer and closer. So stress lines or flow lines closer and closer as the cross section is reduced. Further, if you see at this, when there is an abrupt change in the cross section, you can see there is the bending of the stress lines or flow lines is very sharp, and that would cause a lot of stress concentration at this place. So in order to avoid such kind of scenarios, what people do is, instead of giving a abrupt change at this place, people give a smooth or a gradual change by rounding off this cross-sectional change. And that manner, you see that compared to here and here, this region is closely packed streamlines or stress lines, which can be little bit eased if, instead of having an abrupt change of the cross section, if you give a round off in the cross sectional change. So when there is sudden change in cross section, the bending is very sharp and severe stress is absurd. So by rounding the corners, the stress concentration can be greatly reduced. This is the first case. Now, second one, when the members are in tension, let us put some graphs to it. So in this case, let's say if you have a kind of a V notch on both the things, this is very abrupt changes in the cross section, and there is this, both the ends are subjected to tension. Then you can see that you have the stress line which bends in this given manner across the discontinuities and goes in this manner. So in this not be this one, it can have a kind of hole or a kind of a notch, or it can have several notches as it has been shown. Then depending upon the presence of the discontinuity, it would deflect and it would bend. And so in such cases, it is better to remove. So whatever might, so if I show it for this case, it is better to remove this piece of kind of, if you remove this hashed portion of material, then it is it gives a gradual change in the cross section. So it is a much better manner rather than having a notch, because sometimes notch can go to infinite stresses, because at notch angle more than 270 degrees will give rise to stress singularity that you can learn in theory of elasticity or fracture mechanics. So it is not good. It's not only stress increasing. Sometimes stress can also become singular for different kind of notches depending upon this angle. So instead of having a notch, better to remove that material and create a gradual change in the cross section by cutting off the material in this manner. So in this case, members are in tension with multiple notches or discontinuities. The method is to removal of material that has discontinuities and give gradual change in cross section. So if gradual change in the cross section is resulted, then it would not shoot the stresses to singularity or infinity, and hence it will not cause failure. So better to remove all this portion. Even in this case, either you remove this kind of a material, cause some gradual change, something like this, or remove a material which is within the scope and then create a gradual change. So that is the best manner in which you can avoid the influence of the discontinuities, because this would cause very high stress concentrations as well as stress singularities. Instead of having that, you can as well as give a removal of material to avoid them. Similarly, the third case is, let's say, when you have shafts for reduction of stress concentration. Sometimes we use different kinds of shaft shaft continuations, so that the amount of for the kind of design you are making it. And let us suppose that if you have designed a kind of a shoulder for the shaft connection or shaft continuation in this manner, let's say this shaft is having an abrupt changes like this. This is required maybe because of clearance or something. You want to have a smaller cross section at some places, and you would kind of cut it in this or create an abrupt change in this manner, thinking that this will serve the purpose. But this abrupt change in the cross section will lead into severe stress concentration. In such scenarios, you can reduce the stress concentration arising from these kind of abrupt changes by three different manners. So the first one is using creating fillet radius. So in that manner, instead of a sharp abrupt change, you have a smooth rounding off at this corner, or by doing an undercut at the increased cross section. So this would deflect the stress lines and also the spacing. So that is one way. This is like having undercut, or similarly you can also remove the material not only at this undercut, or you can have a notch at the top portion so that it can also deflect the stress lines smoothly. So otherwise you will have such a wake, this material is kind of wasted and you will have high stress concentration at this end. So this is either by creating a notch, undercut, or fillet radius, one can reduce the kind of stress concentration in these shafts when you have abrupt changes in the cross section. You can also have stress concentrations in keyways. This is the shaft keyways. So let us show a pictorial view. So you can see that because you have this keyway that is present, that would cause the shear stresses in this shafts to be in this abrupt changes, and these are the different contours. The inner contours are deflected less, the outer contours are deflected more, because we know that in the shafts the outer layers take highest stresses. That's the reason we also go for a shallow things. Anyway, we'll come to that at later part when we are designing shafts in the coming sections. Now, in order to reduce this stress concentration or abrupt changes in this manner, there are two ways. The first thing is to drill holes inside this shaft so that it would deflect the stress lines. First is removal. These are the holes. Those are drilled to deflect the contours, stress contours, in such a manner they are gradual in nature. This is one way. Or either you can create, see this is very sharp abrupt change. So here it is like this. So you can change these portions which are abrupt by creating a fillet radius at the corners. So in both the ways one can design stress concentration factors. So, and coming to the other in threaded members, the force flow line. So anyway, let us put the picture first. So in this material, threaded member, force flow line is bent as it passes from the shank portion to the threaded portion, like this. It would deflect in this manner. So the best way to do are two methods. The first thing is here, first one, a small undercut between the shank and threaded portion and a fillet radius provided for the undercut. So by providing undercut, this, instead of having a abrupt change like this, you will have a gradual change, and then so that these portions are not again showing up in the stress concentration, you need to give a small fillet radius. This is one manner. Or in the second one, which is this, is to reduce the shank dia to the core dia. The core dia would be this part is the core dia, so of the thread. And in these cases, you can see that since these parts doesn't participate in the stress concentration or stress to contribute in the stress lines doesn't deflect at all, and this is an ideal situation if you can go for. Okay, so these are the different examples what we have seen in materials or members where you see stress concentrations and how you can mitigate them by taking a small manufacturing considerations like providing um, fillet radius or rounding the corners or removing the material in such a manner that it results in gradual stress flow. So these are the main manufacturing considerations. But even after this removal of materials or these kind of measures one has taken, still sometimes you leave with some amount of stress concentration compared to the normal ones. So in order to deal with it, we have to account for changes in the elementary equations by taking an additional factor of safety by measuring the stress concentrations. And we need to also know that how and in which cases what is the real stress riser we see that is obtained using certain tables and charts. So for that, what we'll do is we will see how this application of stress concentration factors are there, and after that when you are designing it, we'll provide the necessary tables. So if it is a ductile material, in static loading, then the stress concentration doesn't really affect, so not affected by stress concentration. If it is ductile material in dynamical loading, or yes, it is affected by stress concentration. Sometimes, in addition, stress concentration factor notch sensitivity factor is also used. And if it is brittle material, no matter it is static or dynamic, it is always affected severely. So these are the scenarios. So in order to do that, what I will do is I will give you some cases where we need to charts, tables and charts for stress concentration factors. So first one is flat plate with the hole. So you can see here, I will little bit enlarge it. Or maybe it is good not to enlarge it. So you can see that this is for the case, the inset here, the inset over here will tell you what is the type of things you are working on. I will draw it for you. For an example, you have a hole of diameter D and you have a plate W under tension. So under tension / compression. So it can be both either tensile or it can be, I can even reverse it. This is a compression loading picture shown. It is, but as you seen, it is both for the tension and compression. So now, if you know the hole diameter, if you take D divided by W, you know this value. Okay, so let's say if D by W is 0.2, if it is 0.2, you know that the stress concentration factor is 2.5. Now if D by W is 0, that means D is either, that means depending upon, W is kind of infinite or D is very small. In that cases, it is 3 in nature. Or if d by w is, let's say, 0.5, in that case, you know that its value is given by 2.15. So this is for 0.5. This is for the 0.2, which is 2.5 value. This is 2.15. So depending upon this, you can read like that for T by W values. So this is one scenario where plate is under tension or compression. The next one is flat plate with shoulder under tension. So with shoulder under tension or compression. You can find this in any standard textbook. I've taken it from Bandari et al. So in the Bandari book, VB Bandari, you can have in Bandari book, VB Bandari, design of machine elements, you can find such tables. So you can see that this case is a plate with certain thickness has cross-section changes. This is D, this is capital D, and let's say the thickness is something, and this root radius is given by R. So now you can see that for different D by D ratios, this is for D by D of 1.1, this is 1.2, 1.5, and things. So for different D by D ratios and for different R by D, where R is the root radius or fillet radius, which is in the x-axis, you can get the corresponding KT, stress concentration factor here. Right? So if you know this kind of a scenario, you take D over D and R over D and pick the corresponding line. If it falls somewhere in it, you can interpolate it based on these lines. Okay, you can use simple interpolation techniques. So next, shaft, round shaft, shoulder under tension or compression. So this is also pretty similar. In only this thing is earlier both are flat plates. They are joined through fillet radius, whereas these are the circular cross sections. One is a bigger, the bigger D is a bigger circular thing, and this one is a smaller shaft, capital D and small d. And when they are joined together, again you have D by D ratio and R over D ratio at the fillet radius. Depending upon that, you can find the stress concentration factor under tension. Similarly, the shafts can also subjected to bending. So fourth case is stress factors for rounded shaft under shoulder under bending. Now you can see the difference between the above figure and this figure is you can see this loading as bending loading MB, whereas in this figure this is a loading P, which is axial tension is there. That is the difference between the both. And again, this is also based on D by D and R by D ratios for different thing. You look up into these tables or these charts and then determine what is the corresponding KT for this given problem. Okay, so for that, before we end this today's class, we'll take up a couple of examples and then we'll demonstrate how to use it. Okay, now example 1, and that is consider a rectangular plate of 15 mm made of brittle material we need to calculate stress concentration or the stresses at each of these holes of 3, 5 and 10 mm dia as shown in figure below. Let's get the problem description figure. Now for this, we know that this is a flat plate, and for a flat plate we know our W was given by 25, and we know that our thickness is 15 mm, and in the first case our diameter D1 is 3. In the second case our diameter is 5, and in the third case our diameter was 10 mm, and our load P was given as 20 kilonewtons. Further, we know that if you look at this graph which we showed earlier, we need to use this graph, and for that all we need to do is calculate D by W. If you want to, which is the similar case like this, provided we are assuming that each holes are very far from each other, so they are not interacting. So D1 by W is 3 by 25 d2 W is 5 by 25 d3 by W is 10 by 25, right? So So 3 by 25 is approximately 0.12. I will write it as 0.1, and then 5 by is 0.2. It's easier. And 10 by 25 is 0.4. So in this case, the KT let's have to look at the table. So if you look at this table little bit, at 0.1 you have a value of close to 2.7. At 0.2 you have a value of 2.5. And you have 2.25. Okay, but we know that before our definition of K is equals to sigma naught. In all these cases, the fundamental equation says that this is equals to P by A, where P is given by 20 kilonewtons divided by, if I write it in terms of Newton, and area is 25 is the width and 15 is the kind of the thickness of the thing. So it would be like the fundamental equation says that it is 53.33 Newton per mm square. Okay, so as per that, so we know that in this case, first case is 2.7 is equals to sigma max by 53.33. In this case, second case of 3 mm, it is 2.5 is equals to sigma max by 53.33, and this is 2.25 is equals to sigma max by 53.33 for case of 10 mm. Okay, so accordingly we can see that 53.33 into 2.7 is, in the first case, sigma max is equals to 144 approximately Newton per mm square, and this is, in the second case, sigma max is approximately 133.3 Newton per 33 Newton per mm square, and in the last case it is sigma max is equals to 120 Newton per mm square for the, this is for the 10 mm, this is for the 5 mm hole, and this is for the 3 mm hole for a width of a plate which is 25 mm. So this is one example which we have solved, and the next example we will go and solve is a different problem which is very close to this. Subjected to a tensile force as shown in figure below. We'll draw the figure, we'll put the figure. The plate material is grey cast iron Fg 200, and the factor of safety is 2.5. We need to determine the thickness of the plate. So this is the problem that we want to kind of solve. To solve this problem, what we'll do is we'll go and see what are the things that causes the stress concentration. The first one is, this is in a flat plate, there is a shoulder is there with a fillet radius. That is first thing. Second thing is, in this section there is already a hole. So this is one which causes stress concentration, and this is the one which causes the stress concentration. So these two things will cause the stress concentration. So if we design for both the things, and whichever causes the maximum stress, and that will dictate the maximum thickness that is required for this given problem, right? So let us take the first thing is, given things are load P is equals to 5 kilonewtons, and for Fg 200 we know that SUT is 200 Newton per mm square. We know the factor of safety, which is given here as 2.5, and based on that we can calculate the maximum allowable is equals to SUT divided by factor of safety, that is 200 divided by 2.5, which is 80 Newton per mm square. Then we know this is the first critical cross section. So first one flat plate with shoulder and fillet. So we know that at the shoulder the minimum cross section is 30 and the thickness is T, so it is 5000 divided by 30T. Okay, and in this case, if we calculate at the things D by D, which is before the fillet, this is 45, before the shoulder it is 45, after it is 30, 45 by 30, which is 1.5, and fillet radius by D is 5 by 30, which is 1.166 or 1667. So now for this we would go and look for this kind of things. In this we know D by D is 1.5, so 1.5 is this figure, the second one from the top, and R by D is close to 1.7, so let us take, this is 1.12, 0.14, 0.16, and no, this is in 4 divisions, right? So 0.25, 0.5, 0.15, 0.175, so somewhere close to here. So somewhere in between these two, it is around KT is 1.8 coming from this picture. So we know that sigma max is equals to KT times sigma naught, that is 1.8 into our sigma naught in this case is 5000 by 30T, that is equals to 300 divided by T Newton per mm square. Now the second critical section is with the plate with the hole. So for that we know that sigma naught is equals to P divided by the total width is W, the diameter of the hole divided by the thickness, because this gives you effective width. So this is 5000 divided by, we have 30 as the width minus the diameter is 15 of the hole, 30 is the W, D is 15 times thickness is equals to T is the value. Now for the flat plate with a hole, we need to measure D by W. Our D is 15, this is 30, this gives us 0.5. Okay, for that W by D is 0.5, then we see that stress concentration factor in such kind of scenarios is close to 2.15, or we can take it at a higher value, 2.16. So KT is equals to 2.16 from chart, this is flat plate with circular hole under tension. So that is the chart we are seeing. So then we can say that our sigma max is equals to KT into sigma 2.16 and 5000 by 15T. That boils down to 720 by T Newton per mm square. So no matter whatever T is there, from the first scenario, we got sigma max. From the first scenario, we got 300 by T, and from the second scenario, we got 720 by T. So T, for a given thickness, whichever numerator is maximum, that dictates the failure. So the plate with the hole dictates the thing. So this is critical section. So this dictates the design, or this has to be avoided, so that automatically this gets avoided. So we'll take sigma max is equals to 720 by T, but we know that sigma max is 80 Newton per mm square. So if you try to solve this thing, then you can get, and we know this is in Newton, T is in anyway 2 Newton by mm square, where if you don't include T, that is T is in mm, then we can say that T is equals to 9 mm is the thickness that has to be provided so that both the failures can be avoided. So this is how the stress concentration at this as well as the stress concentration of this thing are still avoided, and the design is successfully done for this given case. So this is the one which we have things, and you can also go ahead and proceed for another example if you want to do it. I was planning to take another example. Maybe I will take another example. So the third, so in this, consider a non-rotating shaft supporting a load of 2.5 kilonewton as shown in figure below. We'll put the figure soon. The shaft is made of brittle material with ultimate tensile strength of 300 Newton per mm square, and the factor of safety involved is 3. We need to determine the dimensions of the shaft. So let us have the picture. So we have kind of a symmetric shaft which is non-rotating. We can see that the shaft diameters are changing from D to 1.1 D, and again it kind of abruptly changes back. It again gradually changes to another D with a zero point 0.1 fillet radius. We can see that the shafts which are of D diameter are both sides 350, and the shaft which is of 1.1 D is of 300 in length. And you can see a transverse load of 2.5 kilonewton is subjected. So that means due to these things, we will have bending stresses that will be there in the fillet. Okay, so for that reason, one has to critical design this for the bending values, bending loads. So first let us start. We have a transverse load given as 2.5 kilonewtons, and our SUT is 300 Newton per mm square, and the factor of safety is 3. So the permissible sigma max is obtained as SUT divided by factor of safety. That gives us 300 divided by 3 by 100 Newton per mm square. Then uh, because of the symmetry, we will not be doing entire part of it. So we will assume that uh, by symmetry, you can easily say that this, since it is by symmetry, it is 2.5 kilonewton. That means the reactions at these places are 1.25 kilonewtons by default. So then we can write that our bending because of this has two things. One is the critical sections are at, one is at the center of the span, and second is at the fillet. So the first one, critical sections, this kind of a problem where D to 1.1 D and again it collapses to a thing. It has been transversely loaded by 2.5 kilonewtons. So by symmetry, we can say that the reaction forces are 1.525 kilonewton each. And we have two critical sections. One is at the center of the span and another is at the fillet cross sections. Okay, so now let us consider the case of bending stress at the first case. It is given by 32 MB pi d cube, and where MB at the critical cross section, we can directly write it as by taking the reaction forces 1.25 into 350 plus 150. So that would be like 32 into 1250, it is in kilonewtons, into 500 divided by pi 1.1. The effective cross-sectional center span is 1.1, so it is 1.1. The d is 1.1 d, so 1.1 d whole cube. So that gives you as close to, if you compute it, 4783018618 divided by d cube Newton per mm square. Now similarly, this is at the first section. Now at the second one, your MB is given as 1.25 kilonewton into, the fillet is only at 350 mm, so this is at 350, will give you the bending at that place. So using the same equation, sigma naught is equals to 32 into 1250 into 300 divided by pi d cube is the thing. And but we know that our sigma max at this place is not this, but our sigma max at this place comes as kT into sigma naught. For determining the stress concentration at this change in the cross section, we need to have two ratios. One is d by d ratio, which is equals to 1.1 d divided by d, that is 1.1, and r over d ratio, which is 0.1. So based on these two, if you look into the fourth table, so if you look at the last fourth one at the bottom, and at a value of 0.1 will give you a stress concentration factor of 1.6 from chart. So your sigma max is given as 1.6 into 32 into 1250 300 divided by pi d cube, which comes out to be 7174704 divided by d cube Newton per mm square. If you look at it, both the stresses, this numerator is less than this numerator, so the critical section is the second one, which is at the fillet radius. So sigma fillet max dictates is the critical section out of both, so which is 7174704 d cube is equals to 100. Upon solving this, you get d is equals to 41.6 mm. So if you solve this problem, so in this manner you design your stresses for the stress concentration factor. With this, we will end today's class, and tomorrow we'll again meet and we'll go for the fluctuating loads. So we will meet tomorrow again at 2 p.m. With this, we'll end today's class. Thank you.